Hi, I'm Zoe, and this is my Physics Lab 1. So for introduction, basically for this lab, we had two pieces of tape that we charged, and then we tried to create a floating tape basically from the two like charges repelling from one another, which you can see here. And basically, this is part of the instructions from the lab, and it says that because we need only an approximate answer, we can make two simplifying assumptions. One being that we can assume that each U-tape has the same net charge, and then two, we can treat each tape as if all of its charge were located at a single point at the center of the tape, so basically treating it as a point charge. And these reduce the problem to the one separated in the figure text below, which is not shown. But then these kind of shows the expressions that we're working with. This is the electric force, and this value is what equals to like a constant we call K, and then this is like the charge of the electron. So observations in the lab, it said to draw out a force diagram for the floating portion of tape B. So there's a force of the charge and then the force of gravity. And then this is a computational model of the two charges from the tape. So in calculating the magnitude of one charge on the piece of tape, which is like the goal, so some important things is to find the force, which is mass times the force of gravity, which we got 0.00217 newtons. And then K, which I already talked about, that constant 9 to times 10 to the 9th. And then, so Q equals the square root of the force times 1 over K times R squared, which comes out to equal 1.34 times 10 to the negative 8. See, I already talked about the assumptions. So, some questions. What if electrons had a positive charge and protons had a negative charge? What would you change about the observations made with your tapes and other charged objects? So, the observations wouldn't change because like charges would still repel and unlike charges would attract. However, charges would be described differently because the charges that were negative would now be positive. So there wouldn't really be any visible changes in the experiment. And then why is it important to handle the charged tapes as little as possible? And what happens when the charged tapes come into contact with your hands or other objects? So it's important because you don't want the charge on the tape to go away after touching other objects. For example, the human skin and most surfaces are a lot more conductive relative to air. And so if you handle the charged tapes too much or accidentally touch it with another object, the charge could transfer or be neutralized, which would mess up the experiment. Okay, and then if we go and take a look at the code, I already talked about this, and then you can see the magnitude of the electric force and the magnitude of the gravitational force, and then a little all-done statement. Okay, a lot of this code is like based off of the code from lab 0, and so this represents the K constant, and then this is force of gravity, this is the mass of one tape, this is the estimated net charge on one of the tapes, the length, and then the distance between the tapes that I talked about, like we measure in this part. And then this is the function for the electric field. I'm kind of running out of time here, but the electric field equals the K constant times the net times the charge, and then you divide that by the magnitude of R squared times R hat. And then that's all I have time for right now, but there's like charging the tapes and like the line, and then at the end we print out